Hi everyone, welcome to our next lecture on transformers. Last time we talked about ideal transformers, and in doing so we made quite a few simplifying assumptions to be able to analyze from a high level what a transformer is and what it does. Today we're going to take this one step further. So we're going to talk about real transformers, and we're going to throw away some of those simplifying assumptions that we made earlier. Before we move forward, let's have a refresher of what we talked about last time. In this slide, you see a diagram for an ideal transformer, and as you remember, a transformer is a device that converts electrical energy to electrical energy through a magnetic medium. So if I call this side the primary, here you apply a voltage. This voltage forces some current to flow in the winding, in the primary winding. This is going to be creating some magnetic flux. I show it as phi. That is going to be flowing through the magnetic core. Upon crossing the secondary winding, it's going to be inducing a voltage in the secondary winding. And if I connect some load to my secondary winding, a secondary current that I'm showing here as I2 will be flowing through the circuit. What are some of the important things that we talked about last time? If you remember, we saw that the ratio of the voltage induced in the secondary winding to the one applied to the primary winding is equal to the ratio of the turns of the secondary winding to the primary winding. In other words, I can say V2 over V1 equals N2 over N1. Another important thing that we learned about transformers was the fact that a transformer does not, or I should say an ideal transformer, does not generate or consume power. In other words, the primary power, V1 times I1, equals the secondary power, which is V2 times I2. And we used this characteristics to derive the third important equation, which is the ratio of the current in the secondary winding to the primary winding equals the inverse of the ratio of the number of turns in those windings. In other words, it's going to be N1 divided by N2. These were the three most important equations that we learned about transformers. And in doing this analysis, we made a lot of simplifying assumptions. Now, let's go back to basics and see what are these assumptions, what assumptions hold and what assumptions do not hold. Okay, let's start with the first and most important assumption. For an ideal transformer, we assumed that all the windings are ideal. In other words, we assume that there are no resistances associated with those windings. We know in reality this is not the case. Every winding is going to have some resistance. What does that mean to us? Imagine I have an ideal transformer, and I'm just going to be drawing the primary winding right now. Let's say I apply some voltage V1 to this winding. If the winding is ideal, in other words, if there are no resistance values associated with the winding, the entire electric energy is going to be used to generate magnetic field. In other words, the entire electric energy is going to be converted to magnetic energy. In reality, a winding has some resistance values, meaning that part of that electrical energy which is inputted to the winding is going to be lost in the resistance of the winding. So part of that energy is going to be lost in the form of ohmic losses. So not all that electrical energy is going to be converted to magnetic energy. Later on, we're going to see that this will affect the efficiency of the transformer and how much it is able to convert that electrical energy in the input to electrical energy in the output. But for now, we just remember this. In a real transformer, windings are not ideal, and they have resistance values associated with them, both the primary and the secondary. The second assumption that we made is related to the magnetic flux. If you recall, in an ideal transformer, we assumed that once you connect the primary winding to a voltage source, the current flows through the winding and it's going to be generating a magnetic flux. This magnetic flux will flow through the magnetic core, will cross the secondary winding, and in doing so, it's going to be inducing a voltage in that winding. Well, this is not entirely true. It is true that most of the magnetic flux generated is going to be crossing through the magnetic core and will link the primary winding to the secondary winding, but not all of it does this. Take a look at this diagram. If I apply this voltage V1 to the primary winding, I'm going to have some magnetic flux, let's call it phi. This phi consists of a portion that is going to be linking the primary winding and the secondary winding. I show it as phi of M, M for magnetization. As you can see in this diagram, phi M is the portion that actually goes through the magnetic core. However, a smaller portion of this, a small portion of phi, is going to be crossing through air. It's not going to be crossing through the magnetic core. And here you can see it as this portion and this portion. We call this the leakage flux. The amount of leakage flux does depend on the design of the transformer. So if the windings are very tight and you don't have a lot of open spaces between the winding and the core, you're going to have less leakage flux. However, even in the best designs, even in the most accurate design, you're still going to have some portion of the magnetic flux which is not going to be closing its path through the magnetic core, and instead is going to be crossing through air. And as we will see later on in the future lectures, this is going to be contributing to another portion of losses. In addition to that ohmic losses that we saw in the previous slide related to the resistance of the winding, this is going to be introducing another portion of losses for the operation of the transformer. And this is going to be the case both for the primary winding as well as the secondary winding. So you're going to have leakage flux on both sides. The third simplifying assumption we made about ideal transformers was related to the core itself. We assumed that the core has a linear characteristic. Now, what does that mean? In order to get a better understanding, let's go back to the basics of magnetic circuits. Imagine I have a magnetic core and I have a winding wrapped around it. I then apply a voltage to this winding. As a result, I'm going to have a current I that will flow through the winding. This current is going to be generating what we know as magnetic field intensity, or H. Magnetic field intensity is going to be applied to the magnetic core and will generate magnetic flux density that we know as B. You probably remember from electromagnetics course that B and H are related through a constant mu, which is the permeability of that magnetic material. When we say the core has a linear characteristic, that means the relationship between B and H is linear. That means the more H you apply to the magnetic core, the more B you're going to get. More magnetic flux intensity will give you more magnetic flux density. Some people, instead of a BH curve, they use a phi I curve. So instead of B, they use phi, which is the flux, and instead of H, they use I, the current. Of course, these are related to one another, so it doesn't really change the concept. Now let's go back to basics again and see how this H will generate B for me. I'm going to do a very high-level discussion here. We're not going to dig deep the way you do in electromagnetics course, but just so you have a good understanding of this, a magnetic material consists of many dipoles or magnetic dipoles. These magnetic dipoles are basically a series of NS dipoles, N for north and S for the south pole. So we have these that are essentially randomly distributed. Once you apply the H, or magnetic field intensity, into this material, these magnetic dipoles will try to align with the magnetic field intensity H. The alignment with H is what actually generates magnetic flux density for us. So this is what generates B, or eventually phi for us. If I have a magnetic core with linear characteristics, that means there is no limiting factor. The more H I apply to the magnetic core, or look at it another way, the more current I apply to the winding, I will get more B, or more flux. Now, in a real transformer, this linear relationship between flux and current, or B and H, does not hold anymore. We refer to this phenomenon as saturation. What that means is this. As you increase the amount of current applied to the winding, or the amount of H applied to the magnetic core, you're going to get more and more magnetic dipoles aligned with the H. This is going to generate more magnetic flux for you. There comes a time, however, that most of the existing magnetic dipoles are already aligned with H. So in order to get, let's say, 5% more magnetic flux, increasing the current by 5% or increasing the H by 5% does not suffice anymore. You're going to have to increase the current by a lot more than that in order to get even a little bit of increase in flux. This is because of saturation. Now, before we get to this diagram that I'm showing on this slide, let me explain it to you here. So let's say I have the flux versus current relationship here. If everything was linear, the relationship would have been a straight line. Now here it means that if, for example, you want 5% more magnetic flux, you need 5% more, for example, current. Of course, I'm saying this hypothetically. I mean, the relationship does not need to be 1-to-1. But let's say, for simplicity, it is 1-to-1. So 5% more current is going to give you 5% more magnetic flux. In a real magnetic core, however, there comes a time that most of these magnetic dipoles are already aligned, and you will get to this saturation knee. Here now, if you want to go from here to here, let's say 5% more magnetic flux, you would have to increase the current a lot more than that, a lot more than 5%. Why? Because you have to push the current so much in order to get even a little bit of additional magnetic dipoles being aligned with the H. This is the nonlinear characteristics that you see in pretty much all real-life magnetic cores. Now let's come back to this diagram and see what this means to us. What I have done here is I have shown the magnetic flux here, the red curve on the right, and the current, which I'm calling it here magnetization or magnetizing current, in blue at the bottom. If I apply a sinusoidal voltage to my winding, I know from Faraday's law that the flux is going to be sinusoidal as well, which is why I'm showing this flux here, the red curve, as a pure sinusoid. Now, if everything was linear, if the relationship between the flux and current was linear, when the flux is sinusoidal, current is going to be sinusoidal as well. However, notice that because of saturation, I go a little bit deviate away from the linear characteristics. So here, instead of having points 1, 2, 3, 4, I go to 1, 2, 3, and 4 here. If you find the corresponding points 1, 2, 3, 4 on the BH curve or flux current curve and try to draw it on the other map, on the other graph for the current, you will see that the corresponding magnetization current is going to be something like this. It's going to be distorted. When it is distorted, it means that it's not a pure sinusoid anymore. In other words, it's going to have harmonics. And you will see that this is actually rich in third harmonic and a lot of other odd harmonics. So that is the effect of saturation on a real transformer. The current that flows in the primary winding is not going to be a pure sinusoid anymore. In an ideal transformer, we didn't consider this. We assumed that once you apply a sinusoidal voltage to the primary winding, you're going to get a sinusoidal current. In practice, in real life, however, applying a sinusoidal voltage to the primary winding is going to result in a current which is a little bit distorted. It's not purely sinusoidal. So that's another assumption that we took about ideal transformer, which does not hold true for real transformers. Now, the next assumption, again, is related to the magnetic core. We assume that this magnetic core is ideal in a sense that it has no losses. Real magnetic cores actually have losses associated with them. These losses are not the resistive losses as we're used to in electric circuits. These are magnetic losses. There are two types of losses related to a magnetic core: eddy losses and hysteresis losses. Let's talk about them briefly. So eddy losses are actually a very interesting phenomenon. Consider this magnetic core. Let's say I have a magnetic flux that is crossing the core like this. Once I have the magnetic flux crossing the core, and the core itself is a conductor, using the right-hand rule, if this is the direction of the flux, let me show it in front of the camera. If this is the direction of the flux, my four fingers will show the direction of the current that is going to be induced in that conductor as a result of the flux. So I will have currents that will be circulating in this direction. Now again, remember that the magnetic core itself is a metal, is a conductor. It's going to have some resistance values, and you're going to have circulating currents flowing in that conductor. This is going to be generating resistive losses, just like any other conductor. Resistive losses means heat, and heat means basically a reduction of effective lifetime of your transformer. So that's one source of losses in a real transformer. Of course, the reality is not as bad as I'm showing it here, because what manufacturers typically do is, instead of having a bulk of magnetic core, they actually build one using sheets of metal. So you're going to have one sheet of metal, and then next to it, it's going to have a sheet of an insulator, and then another sheet of metal, and another sheet of insulator, and so on. What the insulator does is it kind of puts up a resistance against the circulating current, so it kind of reduces the amount of current that can actually flow in the core, and hence it reduces the amount of losses. Hysteresis losses, on the other hand, are another interesting phenomena that happens in magnetic cores. Now, in order to understand hysteresis losses, again, we have to go back to the basics of magnetic circuits. Let's consider a magnetic core with the saturation curve. So let's say in the beginning, when I haven't applied any current to this winding, or haven't applied any H to my magnetic core, all the magnetic dipoles are randomly distributed, and they kind of cancel each other out. So I don't really have a net magnetic flux in my core. As I start increasing the current, the magnetic dipoles will try to align with the magnetic field intensity H, and will generate flux. And of course, I get to the point which is a saturation knee, at which point I would have to increase the current by a large amount in order to get even a little bit of increase in phi in the flux. But let's say this is how I operate. Now imagine, instead of applying just a positive voltage to this winding, I apply a sinusoidal voltage. So now I have my positive half cycle and the negative half cycle. So in the positive half cycle, I apply the voltage that goes up and up and up until I get to the peak of the sinusoid. Here the current increases, H increases as a result, meaning that the magnetic dipoles will try to align to the maximum amount that they can. That will give me the maximum flux. Now I'm reducing the voltage, hence the current. So the magnetic dipoles will go back, all of them, to their original state, which was, canceling each other out, zero magnetic flux. Then I go to the negative direction. So now all these randomly distributed magnetic dipoles will try to align in the opposite direction. So if I continue this, I will get something like this. So I will go up, and then I will come down and go down here, and then again come back up, and I continue this loop. So this is a core that does not have the hysteresis effect. But what is hysteresis effect? Let's go back to the magnetic dipoles. I will start from a random distribution of magnetic dipoles, which, let's say, it gives me zero magnetic flux. We all agree with that. But as I increase the current, and I get to some point, which is, let's say this point A, which is the maximum current and maximum flux. If I start reducing the voltage and the current, the flux is going to reduce, obviously, because all the magnetic dipoles will try to change their alignment. However, can I really assume that I start from random distribution, go to all alignments, and once I reduce the voltage, I go back from all of them aligned to exactly the same random distribution? Well, this is not reasonable. I will go to some other random distribution, but definitely not the original one if it was truly random. So in practice, what happens is this. I will go from here to here by increasing the voltage and the current. Once I start reducing the voltage and the current, instead of going back exactly along the same path, I will go back through a different path. So once I have no current applied to my winding, hence no H in the circuit, I still have, as you can see here, a little bit of magnetic flux. Why? Because maybe now the dipoles have been distributed in a way that they do not exactly cancel each other out like before. Because a random state that I start with is different from the random state that I end at here. Then, by reducing the voltage and going to the negative half cycle, let's say I come to this point, which is point B. So this is point A, this is point B. Now this is the negative peak of the voltage. If I start increasing the voltage again, I will not go back through the same loop, and I will go through a different path. Now this is going to be a loop rather than a line here. So here, as you can see, I have a path that I follow exactly in the positive and negative half cycles. Here on the right hand side, I have a loop rather, so it's not exactly the same path that I follow. This loop is called the hysteresis loop. And there are losses associated with this phenomena in magnetic cores. Some people use the analogy of friction between the magnetic dipoles, as if there is friction once they want to go from random distribution to full alignment, and then going back from full alignment to random distribution. Of course, you understand that there is no friction because this is not a mechanical circuit, but that's the analogy that we use. And we say that there's going to be losses, magnetic losses, associated with the area under this magnetization curve, the hysteresis loop. So now when you connect a magnetic core, you wrap a winding around it and connect it to a voltage supply, the current that flows through the circuit has two roles. One role is to magnetize this core by generating a magnetic field intensity and a magnetic flux density B and a magnetic flux. That's what we refer to as magnetization current. Another portion of it now, based on the discussion we had just now, is going to be used to basically overcome the losses in the core, which is eddy losses and hysteresis losses. So now, from now on, we're going to be referring to the total current as the excitation current. That's the current that excites the magnetic core. Part of it is going to be IM, magnetization current, which is used to magnetize that core. Another part, I refer to it as I of C, the core loss current. This is the current that tries to overcome the magnetic losses in the core, and based on our discussion, consists of a portion that has to overcome hysteresis losses and a portion that has to overcome eddy losses. The fifth and the last assumption that we made about ideal transformers, again, was related to the core. We assumed that the magnetic core is magnetically ideal. In other words, we assumed that its permeability is infinity. Permeability is the measure of how ready the material is to receive magnetic field and generate magnetic flux. Again, if you recall, B is going to be mu times H, so that mu is the magnetic permeability. So if I draw the curve, the BH curve, if the material is not very much receptive of a magnetic field and cannot generate a lot of magnetic flux as a result, mu is going to be small, so the curve is going to be like this. If you have a better magnetic material, mu is going to be larger. That means that with the same amount of H, you're going to be able to generate more B, and a better material and a better material. So that mu indicates, how well this magnetic core can generate magnetic flux. In ideal transformers, for simplicity, we assume that mu is infinity. So here, we assume that for the primary, I have N1, I1, and for the secondary, I have an MMF of N2, I2, and there is nothing in between because the core is ideal. If it is ideal, I'm assuming that it's not going to put up a resistance against the magnetic flux, so everything is going to be linking the two windings and everything is going to be ideal. And if I consider the fact that N1 I1 equals N2 I2, I will get the famous equation that N1 to N2 is I1 to I2 to I1. That's one of the main equations that we came up with. If in the core, however, permeability is not infinity, that means the core is going to be putting up some level of reluctance, which is the equivalent of resistance in magnetic circuits. So now, in between, I'm going to have a reluctance value. Again, I'm not going to go into details of this. You probably remember from your electromagnetics courses that if I have a core with a length L and a cross-sectional area A, the reluctance value is going to be L divided by mu times A. Obviously, when core is ideal and mu is infinity, that reluctance value is 0, so I will get to where I was for an ideal transformer. If the core is non-ideal, however, if you write the KVL in this equivalent circuit, you will have N1I1 minus N2I2. Instead of being 0, it's going to be R times the flux, the magnetization flux. What does that mean to us? The only thing it means to us is this relationship of I2 to I1 equals N1 to N2. This is not going to be exact, but it's going to be approximate. So instead of saying I1 to I2 is going to be exactly equal to 1 over A, I can say it's almost equal to 1 over A. So that's the only difference between an ideal transformer and a real transformer. So that brings us to the end of this lecture. Here we talked about 5 assumptions that we made about ideal transformers that do not hold true for real transformers. In the next lecture, we're going to be using all this information in order to derive an equivalent circuit for the transformer. Again, like before, the book by Chapman, Electric Machinery Fundamentals, is the main reference that I have been using for these lectures on transformers. I encourage you to refer to that for more information on the material that we discussed. If you have any questions, please write a comment in the comment section, and I'll try to respond to that as quickly as possible. Thank you, and I'll see you in the next lecture.